So can I proceed? Okay, welcome to day 3. Can you mute? Welcome to day 3. It's yet another great day for us to move on with our training. Like the assignment we had yesterday that was left with by Professor Susan, we are going to have 2 people to present, or 3, about the work that she left, and then we'll start the day's business. I ask David to give rise to two or three participants to show what they learned yesterday. Professor Susan.
Good morning, participants. I hope you had a good night and you took some time off to go through the assignment. I'm saying good morning, and I hope you had some time to go through the assignment. I left one question for you to go through. So I was requesting if somebody went through the assignment and would like to present to others, you can either raise up your hand or you can write in the chat. Then David will give you a right to share.
Farai, I've promoted Farai Faustus Mashiri.
Okay.
Farai, please unmute yourself.
Oh, can you hear me? Can you hear me? Good
Go
morning.
ahead.
Hello.
Hello, go ahead and present.
Okay, all right. Let me share my ARA studio. Okay, just a moment. Okay, can you see my screen?
Yes, we can see.
Okay, so what I did is I started with data entry, like the data that we were given for sheep and for steers. I had to enter
You
it.
can increase your voice and also zoom in your R script.
Okay.
Can you zoom in so that the words become larger? Now you go to view and zoom in.
Okay, view.
Then zoom in. View, zoom in. Yes.
Is it bigger now? Is
Yeah,
it
that
better?
is okay. That is fine.
Okay, all right. So I was saying I started by doing data entry, where I entered data for sheep and for data for steers. Then after that, I had to convert this data into a data frame using the as data frame function. Then also binding the 2 vectors together, the one for sheep and for steers. I used the cbind function. Okay. All right. So that was the first thing I did.
Okay.
Then for the first question that says what kind of tests can be done, I assumed we are supposed to use the t-test for independent samples,
Okay.
the unpaired one. Okay.
Yes.
Then for question number B, what are the assumptions? These are the assumptions. There should be normal distribution in our populations. We are supposed to be having small samples of less than 30, right? Our samples should be randomly selected, and samples are independent of each other. Right? Then the variance are equal. In other words, we are saying the variance of sheep, our data for sheep is equal to the variance for our data for steers. Right? Then because of that, we have to test that that assumption using the var test the var test function, where we say var test sheep and steers. Right? When I ran this,
Increase your voice. Increase your voice. They can't hear you very well.
All right. Maybe let me try and change my mic. Let me try and change my mic. Can you hear me better?
Yes, you have a background noise behind.
Okay.
Okay, I think that stopped. You can go ahead.
Okay, all right. So I was saying, because of we have the equal variance assumption, what we have to do is to test that variance using the var test function. Okay, right. When I ran that that function, I found out. Let me. Can I just run my code? Let me run.
Go ahead.
So that we can see the results.
Yes.
Okay.
Okay, go ahead.
All right, I'm right. So this is the result for the var test. My p-value is 0.5211, which is higher than the 0.05 threshold. So what that means is there are more chances that the variances are the same. So because of that, we have no ground to reject the null hypothesis that says the variances are the same. In other words, we are going to accept the null hypothesis and say that the variance for the sheep data and that for the steers data are equal. All right. So I move on to C.
Okay, go ahead.
Yeah. My null hypothesis is that the two means for the sheep and the steers are equal at 95% confidence level. That will be my null hypothesis. Then for D, I'm going to run the t-test. This is how I did it. I used the t.test function. Then I specified the two data columns, which is one for sheep and the one for steers. My mu is equal to 0. Then paired is equal to false, because these are independent data sets. Var equal will be equal to true, because we just tested the assumption and found out that the variances are equal. The confidence level is 0.05. So let me run this one. Right, when I run it, this is my result, where the p-value is 0.06368. So because the p-value is less than alpha 0.05, we can reject the null hypothesis that says the means of sheep and steers are the same. In conclusion, we can say that because we have rejected the null hypothesis, that means the mean for sheep is significantly bigger than the mean for steers at 95% confidence level, right? The reason why I'm saying it's bigger is because when we ran our t-test, with here at the bottom, it's telling us that the mean of x is 56.21 429. The one for y is 60. Okay, so actually I made a mistake. It should be the mean for sheep is smaller because it's 56. It's smaller than the one for the steers. Okay, that's my presentation.
Thank you very much. That was an excellent job done. I saw some questions in the chat saying that you can tell them under your command test.test. Why do you use mu is equal to 0?
Why I'm using mu is equal to 0 is because this is a two-tailed test. It's not one-sided, so I use mu is equal to 0.
Okay, mu is equal to 0 is actually the null hypothesis. It is being specified, mu is equal to 0. Then another one said, is the script okay? The script is fine. And I would like to thank you for a great job done. You answered all the questions correctly. Well done. Thank you very much.
Okay, thank you, Prof.
Yeah, you can stop sharing, or you can actually share your script with others if they want to see what you did, because we are not going to go through it, because whatever you have explained is what I would have told them. Let's have another person sharing, and then we go to another person.
Prof, I promoted Dennis Wamalabe. Dennis,
Hello,
please go ahead.
Hello. Hello.
Yes, can you share? Yes, we can hear you.
Okay, mine was just a comment on what the previous colleague was presenting.
Yes.
On the means, he noted that statistically, he said that the mean difference for the sheep is smaller to that compared to the steers.
Yes.
Will it be that like just for the like the term used smaller? Do we say smaller statistically, or do we say like it means a threshold of statistical significance?
First of all, the results show that the two values are statistically significant, meaning they are different.
Yes.
They are statistically different. And now he's giving you another insight. Instead of stopping you, he's telling you that one of the two has a higher weight than the other. And he's telling you that the sheep has a lower weight than the steers. So he's like writing up the results.
Oh, so it's,
go ahead.
It is a substantive point of what the statistics have said.
Yes, he's just
right.
He's just making a conclusion for a layman's person to choose whether he should feed steers with the dry matter.
Oh, thank you. That was my concern, Prof.
Okay, thank you. Any other person who can present, please? Can we have one more person?
I promoted Elias Yusuf.
Okay. Okay.
Yusuf, please unmute yourself and go ahead.
Okay. Good morning to everyone. Thank you.
Good morning.
Professor.
Can you share your script or your Word document wherever you have the info?
Okay, I'm sharing my screen.
Okay. And zoom in so that it becomes a bit wider.
Okay.
You can go to view, zoom in, yeah. Zoom in, yes. Again. Okay, I think that's okay.
I presume it's, yeah. Okay, so the questions were for us to find, I just asked the previous presenter, it was on paired sample t-test, and the assumptions were that they are normally distributed, small sample size, as the two samples there for the steer and for the ship were less than 30. I think 7 entries for each. And they were independent of each other. The variances, it's assumed that the variances are equal. So my hypothesis here was that the coefficient of digestibility in ship and in the steers are not different, they are equal.
Okay.
So I loaded these libraries, and then with my directory, I set, actually here I had a problem reading I entered the data in Excel, but then when I converted into CSV, it would give some characters whenever I try to read the heads. Especially for the ship, there will be other characters that will come there, and I thought it was not going to give me a smooth working process. So I tried the Excel format, and it worked. It didn't. So if I can view my data.
So you can talk as you run the, yes, okay, thank you.
Yeah, so here on the ship, I realized that there were some 3 different characters that were joining, preceding the word ship. So that is the reason why I changed the extension, the file extension to Excel instead of the CSV as we were taught. Yeah.
Okay.
So let me clear my console. I run. Yeah, so the heads. Let me close this.
Okay.
And then this is my data structure. They are numerical in nature, the 2 samples.
Okay.
And then I just try to do the summary. But then in comparing the 2 means, I tested for the equality of the variances.
Okay.
And so the equality of the variances gave me a p-value which was not significant, meaning they are equal and not different. So I was able to go ahead to perform the t-test on the digestibility of both ship and then steers.
Okay.
And my MU was the null hypothesis, which was that they are not different from the digestibility coefficient between the two, the ship and the steers are not different. So the MU stayed 0, and then I run.
Okay.
So when I run, yeah, so upon running, I got a p-value of a significant p-value, which was less than 0.00,
Mm-hmm.
0.05
Yes.
significant level.
Mm.
So it confirmed that the null hypothesis needed to be rejected, as the p-value is saying that they are different, statistically different. So if you look at the means of the steers and the means of the ship, that of the steers were significantly higher. The coefficient of digestibility in steers are significantly higher than that of the ship.
Okay.
Yeah, so that is my presentation here.
Thank you very, very much. I am so delighted and excited to see that you two people have done a great job. That means we are not really talking, not seeing your faces, but you're really understanding. Well done, Yusuf.
Okay, thank you.
You can
Yes.
share your script with others using the chat,
Okay.
those who want to receive. I wanted you to make a comment. Somebody sent a comment in the chat that they still don't understand how to reject the null hypothesis or when to reject the null hypothesis. Can you make a comment on that?
Yeah, so with the null hypothesis, I want to highlight in blue the hypothesis that I tested here. So the sample t-test here assumes that the assumption is that the equality, the variance of the two, of the two samples are equal. So you are testing the hypothesis that, I have the hypothesis here, that the coefficient of digestibility in the ship and in the steers are the same. There is no statistical differences between the coefficients, whether the ship or the steer. So if you test the hypothesis and then you have a significant p-value here, in this case, it was this highlighted in blue. So my confidence interval was 95%. So at this rate, I have a p-value which is less than 0.05% significant level. So there is enough evidence for me to reject the already stated hypothesis that there is no difference. The p-value here says it is different significantly at 0.006, which is less than the 5% stated. So this means the means of the steer, the X represents the mean for the ship and the Y for the steer. So with this result, the p-value indicates that the 60.9 is significantly higher than the 56.2 coefficient of digestibility in ship. Yeah, so that's what my submission on that. Thank you.
Okay, thank you so much, Yusuf. I hope it's now clear to participants when do we reject the null and when do we fail to reject the null. Thank you so much. Please share your script with others in the chat. And let's now continue with the paired t-test, and then from there we go to analysis of variance. Okay, so I'm going to share my script for paired variance. Huh? What?
they are the two data sets set independently or combined as one population?
What do they mean? Kawandike sikutegeera. Okay, ladies and gentlemen, yesterday we looked at t-test and we were left with looking at the paired t-test. That's what we are going to do. But as usual, when you start R, you first of all run your library. So please also open your computers. Make sure you have the script app, which is called Follow-up 0. That is the file. And then follow what I'm doing. Then after we finish the pair t-test, we'll go through a theory of analysis of variance. Then we come back to practicals for analysis of variance. And I'm assuming that everybody received their notes because we sent them last evening. So I ran all those packages. You wait a bit for them to run. Then I'm scrolling to paired t-test. When you run the packages and you see the red notes, just read what the red notes say. Sometimes this package is successfully loaded, but the red points are just information for you not to worry about the package, unless if it says it has failed to what? To load. That's when you get worried. So we have this last part of the t-test, and it is called the paired t-test. And yesterday I was telling you that for you to conduct a paired t-test, you must have collected data from the same experimental unit, either over time, or you measured the same experimental unit. You measured maybe the size of the head and then the length of the arm. You see what I mean? So when you measure the size of the head of a human being and the length of the arm, the two things are correlated because the chemical reactions happening in a human being also go to the hand as well as the head. So that correlation there makes the information you collect on one experimental unit correlated. That's why we cannot perform a two independent t-test. Now, the data that we are going to use was collected on 13 plants. And then on those 13 plants, they got the weight on the top of the plant and the bottom part of the plant. So it is the same plant which is being measured twice. So in that type of data, there is correlation. You can actually prove whether the correlation is there by using the correlation function, as we shall see in regression. Okay? So we are going now to, first of all, set the directorate. We go and set the directorate. So I'll go to session window, set working directorate, and choose directorate. So that's where I am, and I'm going to click choose directorate. Then I browse to where my folders are and choose follow-up. So follow-up is where my data sets are. So you browse to where your data sets are. Okay? So that's where you browse to. So we've finished setting our directorate to where you've stored your data. Okay? Now, after setting the directorate, I have loaded the packages which I require to run my analysis. Now I got to read my data. When you enter your data in an Excel worksheet and you're saving, make sure you choose CVS Limited and then save it, and make sure when they ask you that, do you want the font from the previous formats to be saved, you say okay. So when you read it in R, it doesn't give you problems. And when it says save again, don't save again, so that you don't get problems reading it in R. Okay, so let's read the data. I'm assuming that everybody is at this stage of reading the data in R. Is that correct? Should I assume so? Let me look at the chart. Okay. Okay, somebody says I give 2 minutes. Okay. Not yet. The assumption is true. Okay, thank you. Which file? The file is called wait. I don't have the script. That means you don't have the email address with us. Okay? Okay, I'm going to give you 2 minutes, please. After 2 minutes, I'm going to go back to the chat and ask, do you have the script? Do you have the data weight? Because it was sent on Monday. It is the same script. And once we finish paired t-test, we have data sets we sent yesterday for analysis of variance. So make sure you have all the work that we sent yesterday. If you've just joined, my colleague can try to paste the data sets in the chat and you pick them if possible. And also the script, but the script for t-test, if she can find it, then she will also paste it there in the script and the Q&A. Okay, so that's enough time for you. I'm thinking that you are all okay. Is that true? Is the assumption true? So that we go ahead. Okay, great. So we are going to go ahead with pair t-test. So the first line here is to read in the data. So I just click run and it is reading the data in. Okay. Then the second line is to show the first 6 rows of my data is called head weight. So I click and you can see the first 6 data sets and how, sorry about that, and how the variables have been written. The reason why you use head is also to see how these variables have been written. Are there capital letters, underscore, etc. So make sure you know how your variables were written in the file where the data was saved. Then, as usual, when you get a data set, do summary statistics. You do some graphs and do some summaries, numerical summaries, to have a feel of your data, to see whether there are differences. Is it worth conducting a pair t-test? If you find that the bottom weight is maybe 80 and the top weight is 81, should you go ahead and conduct a t-test? That's the reason why we do descriptive statistics. Or you can construct box plots or graphs and see whether there's a trend, and that is the trend you want now to test whether it statistically exists. So for you to perform inferential statistics, don't just go in and perform inferential statistics. Make sure that actually there is a reason for you to go and do a paired t-test. So we are going to run the row of summary. Okay. My colleague says she has sent all the data and all the information you need for today in the chat. So make sure you capture it before it disappears. Okay, so if you look at the bottom in the console, we see that we've gotten a summary of our data. You can actually present this in your project. What you do, make sure that you have only one column of the statistics you've calculated, then you have bottom and top. So you don't need all these things in between. So you can eliminate this and make sure you have the minimum and look at the bottom weight. The minimum weight is 78 for both bottom and top. The first quarter is 83 for bottom and 82 for top. The median is 87 for bottom and the top has 82. The mean is 86.38 and Here the mean is 83.23. Who can tell me? Okay, I will not ask this question, but maybe you can post the answer in the chat. If the mean and the median are equal, what would we talk about the distribution of such data? Can we see in the chat some answers? If the mean and the median are similar, what would we say about the distribution of the data? Linear distribution, even distribution, normal distribution. Since here I can't follow, I don't know the notes. Okay, normal distribution, normal, skewness. Okay, great. Thank you so much. Somebody said they can't follow. I request Helen to post the data set and the script so that this person can follow. Okay, let's go back to the output. The bottom weight median is 87 and the mean is 86.38. We can see that there is no significant difference. They are not so much different. They are within the same range. And I asked a question, if the mean and the median are similar, that means that that distribution is normal distribution. So even if you don't construct a normal probability plot, only the magnitude of the median and mean will tell you that the distribution is normal. So that assumption we don't even need to test. Now, if the mean was greater than the median, then our data would be skewed to the right. And if the mean was less than the median, our data would be skewed to the left. I repeat, if the median and the mean are similar, then the data is normally distributed. And if the mean is greater than the median, then the data is skewed to the right. And if the mean is less than the median, the data is skewed to the left. Okay, that was just a hint on if you're writing your project, you've produced summary statistics, you can write a lot about it. We can also look at the maximum. We see that the maximum weight for the bottom is 92 and the top is 93. So there are differences actually in weight of seeds for both bottom and top. So I'm now writing my project. I'm saying there are observed differences between the weight of the bottom and the weight of the top. So I'm going to conduct a paired t-test to find out whether this difference is statistically significant. So now I go to t.test. Okay, so accompanying this, I put paired equals true because it's what I want to conduct. So now let's run the paired t-test. Okay, so we have our results. Paired t-test. So the results are in the bottom left corner. They are highlighted in blue. If you're colorblind, then I can remove the blue, but I don't think so. I believe that nobody is colorblind. Okay, so we receive a t-value. So I'm going to highlight the results. So now we can pick these results. Okay, the one I've highlighted, and paste it in your Word document, and you start writing around it. We've received a t-value of 2.9718. We have degrees of freedom 12 because our values were 13. And in a paired t-test, what happens is that we get the difference between bottom and top. Then we perform a one sample t-test on the differences. That's why you see the degrees of freedom is 12, which is different from the two sample t-test. Then the p-value is 0.011. The hypothesis we are testing is that the bottom, the weight, or we can say there is no variation in weight of the bottom and the top seeds of the plant, or there is variation in the weight of the seeds for bottom and top, or you can see there is no difference okay? Or we can say that the bottom weight of seeds is likely to be the same as the top weight. Depends on how you want to write the English now. It is about English and the research you're working on. So we said yesterday that the significance level you set, 5%, it is the probability that the null hypothesis is likely to be correct, okay? It's assumed to be correct or true. Now, if we get any p-value from our results smaller than 0.05, then the chances that the null is likely to be true is decreasing, is disappearing, meaning that we have evidence to reject the null and conclude that actually the mean of bottom and top are different, are statistically different. And after that, you can have a confidence interval attached to your mean difference. So we have the mean difference confidence interval. It ranges from 0.84 to 5.466. So this is a range of possible values for the true population mean difference between the bottom weight and the top weight of seeds for the plants. So that is the paired t-test, as simple as that. Any question? Any question? Let me check the chat. Huh? Okay, let me see. Error in that. I repeat my explanation. Okay. Okay. Okay, so let me check the Q&A and see error in test dot. Why is missing for paired test? Why should there be an error? Okay. Okay, so some people have said, can I repeat the interpretation? Others are saying it's clear. So for the purposes of the minority, I am going to repeat the explanation. And I've said we are testing a hypothesis that the weight, there's no variation in weight of seeds for the bottom and top. And the alternative is that there is variation of the weight of seeds for bottom and top. Okay, then when we perform our paired t-test, we get a p-value 0.011. Remember that we've set our p-value at 0.05. That is the significance level that you researchers set for yourself. And whatever you set, you remember that is the amount of error you're making in your conclusion. So if you're saying that at 5%, there is a significant difference between the weight of bottom and top, that implies that you're 95% confident that there is significant difference in the weight of the bottom and weight of the top. But 5% of the times, there are no differences. So when you specify your significance level, remember that if you make it big, 10%, you're going to make 10% error in your conclusions. So we are going to compare the calculated p-value, which is 0.01166 from your output, with our significance level of 0.05. So if we get anything less than 0.05, then we know that there is evidence to reject the null and conclude that there are significant differences between the weight of the seeds for the bottom and top. And I also went ahead and said you can actually attach a confidence interval. And the confidence interval is the confidence interval of the difference between bottom and weight. So I've highlighted it in blue, and it ranges from 0.84 rounded off to 5.466. So we find that this is a range of possible values within which the true mean difference lies. Okay? And if this difference, you can see we are subtracting bottom minus top using alphabetical order. So you can see if this difference was negative, it would imply that the weight of bottom is less than the weight of top. But this difference is positive. It implies the weight of the bottom seeds is significantly higher than the weight of the top seeds. Is that clear? Let me check the chart. Can we go ahead? Is that clear? Pardon? Okay. There's a question, is there a way of changing the p-value in R? This calculated p-value corresponds to the t-value you got. Okay? So if you want to change this p-value, then you need to change your data, which is not ethical. So this p-value here cannot be changed. The only value you can change, the probability, is the significance level. And you have also to give reasons why you're shifting from 0.05 to 10%. As a student, sometimes you want everything to be significant. Or as a researcher, you want things to be significant. It is easier to defend significant things than non-significant things. But don't be tempted to change, because there is ethics in research. Okay? So if it is a spade, call it a spade, not a big spoon. Okay? Okay, so now we've finished with the t-test, and I want us to shift a little bit and go into analysis of variance. We find that the aim of the t-test is to find out whether there are differences between two groups, one or two groups. Now, when you have more than two groups, then we cannot use the t-test. There are problems when you use a t-test for many groups, which we shall see as we talk today. Okay, so we are now going to go to the PowerPoint. So all of you, let's shift our eyes to the PowerPoint and look at the analysis of variance PowerPoint, which I sent yesterday. So I'm going to stop sharing this. Then I share something else. Okay, so we are going to look at analysis of variance. And analysis of variance, before I go to this slide, it is a statistical method used to compare more than two means or two groups of populations. We have one-way, two-way, three-way, depending on your design. This is just a hint that when you're doing analysis, make sure that the type of statistical method you choose goes hand in hand with the method of data collection. Now, assuming that you conducted your study and performed a survey and you collected percentages, you had more than two groups, you can also perform an analysis of variance so long as the sampling units were selected randomly. Okay? But when we are writing our proposal, we should actually know how to analyze our data before we collect it. So when you do that, your life becomes very easy. So as I go to the next slide, I'll tell you that when I was doing my PhD, I wrote my proposal in my first year and sent it out for funding because I didn't have funding. And then I started reviewing literature, but that proposal was fully written, including the type of analysis. You'll say because I knew, but I was also a student, just like you, okay? So when you write your proposal and think through it, review a lot of literature, you will be able to know the correct or the proposed method of analysis. And when you know it, things become so swift because it's analysis which makes people delay either to publish or to finish their degrees. So once you know the method of analysis, which goes in hand with the data collection method, the data collection method goes hand in hand with objective. So that sums up our research process, which is cyclic. You start with a problem and you end up with a problem. So if your analysis method is different from your method of collection, then you're not going to get the correct results to answer your objectives. And also make sure that the variables that you are putting up are actually the answers you want for your objectives. So that's just a by the way. Let's go to the real thing, analysis of variance. Some people were asking about analysis of variance on their first day. And the thing is, when you are teaching a child to walk, you don't start by making them run. You start by making them move one step, one leg and the other, and then you let them go and they walk. So if we had started with analysis of variance, we would have less people than today. But now you've been used to the R commands, you're used to statistics. The brain now is tuned in for more. It's yearning in for more, so we are also going to give you more. Okay, now, the reason why I brought in experimental design here instead of talking of one-way analysis of variance is to show you that complete randomized design is performed when the background conditions can be controlled during the experiment. So in this case, we have experimental units which are randomly allocated to the treatments. Okay, so we could have one factor that we are looking at or one treatment. For example, we have species and we are looking at the growth, or we have variety of corn and we are looking at yield. So once we've set up our experiment, we have a background conditions controlled and we only have one factor, then we can perform an analysis of variance. Now for a CRD, this is a by the way, I have written this for your information that we have a model, which is a simple model, where the Yij is the observed response from treatment I, mu is the overall mean of the observed response, tau I is the effect of the treatment on the response, and epsilon ij is the experimental error. So for each unit, experimental unit, we have an epsilon, we have the error, which is called residual in some cases, or unexplained variation under regression. Okay, now the hypothesis that we test. Remember in t-test, we looked at two groups. So our hypothesis was that mu is equal to mu naught for one sample t-test, or mu is equal to mu A is equal to mu B for two sample t-test, and for pair t-test, we are looking at the difference. Mu D is equal to 0. Now here, because we are looking at more than one mean, our null hypothesis is that there is no difference. Overall, we do not have differences among the treatments. And then alternative says that not all means are equal, or at least one of the means is different. At least one of the means. Can please correct that? There is a typo here. At least one of the means is different. Okay. So analysis of variance, abbreviated as Anova, is a statistical technique used to compare more than two population means by isolating the source of variation. The analysis of variance divides the total variation into between variation and within variation. That is for a one-way analysis of variance. Why is it called one way? Because we have one factor. If we have more than one factor, then it's going to change and become a two-way analysis of variance. So one-way analysis of variance, we have one factor. Maybe we are looking at the different cultivars. So we have cultivar as our treatment, and we have 5 of them, and we are testing them against, we are looking at their performance in a particular place where we've controlled the other factors, meaning that the only factor we are concerned about is cultivar. Okay? So in that case, if we have only one factor, one treatment we are looking at, we use one-way analysis of variance. So the treatment variation, that is the variation that is explained by the treatment once you conduct an analysis of variance. And residual is what remains. That is the variation due to other factors not included in treatments. Okay? So the amount of variation that remains out of the total is what we call unexplained, residual, experimental error. All those names mean one thing. Okay? So, Anova compares means among groups defined by a categorical variable. Now, we find that there is a relationship between Anova and regression. Anova, we have categorical variables for independent variables. So in Anova, one-way analysis of variance, we are going to have one treatment which is categorical, for example, cultivar or variety or species, but also this variable could be quantitative, for example, levels of fertilizer. Then in regression, we can have one independent variable, but in this case, they are continuous, depending on the type of regression. But both of them are special cases of the general linear model, which we are going to abbreviate as LM in R. Okay? And the general linear model I'll take you back is this particular one on slide number 2, which I'm showing you. In this case, we can see we have mu, which is the overall mean, the effect of the treatment, and the unexplained variation or experimental error. So the same thing you're going to observe when you look at regression, probably tomorrow. Okay. So this is a table for one-way analysis of variance. We've talked of the between variation. I'm going to use the cursor and I will circle around what I'm talking about. The source of variation here, we have the between, which is we are calling treatment variation. And then here we have error or residual, which we are calling residual variation. And total is the total variation. We also have what we call degrees of freedom. And the degrees of freedom for treatment is the number of treatments minus 1. The degrees of freedom for residual is the number of observations or number of experimental units minus the number of treatments. The total is n minus 1. In all these, the reason why they are subtracting depends on the number of parameters you are computing in order to compute the mean of the treatment. For example, here, for mean, we require only one parameter. Sums of square, we require also one parameter, which is the mean. Here, we need all these parameters for all the treatments. That's why we are subtracting t. Here, under sums of squares, we only need mu. Okay, the overall mean is what we need to compute our sums of squares for total. So that's why you see t minus 1, n minus t, and n minus 1. Under regression, as you will see, in this part, we will have n minus p, meaning the number of parameters in the model. Here we have n minus t, the number of treatments in the model. So for each treatment, you calculate a mean, which you use to compute the sums of squares for error. Okay, then we have sums of squares. They are formulas, but this is purely science, so we are going not to put formulas in here. And then we have mean square. We have the treatment mean square, which is the ratio of sums of squares and degrees of freedom. So if we take sums of squares for treatment, divide by t minus 1, we get the mean square treatment. Then the error mean square, we get the sums of squares for error and divide by the degrees of freedom for error. Why do I have to go all through this? When you do your analysis using a computer, you should know what the computer is doing. Don't just take what they've given you. So you can look at the simplest way to know whether your analysis is correct is look at the degrees of freedom. Once they are correct, then all the others are correct. So that's why I'm going through this table. So you can actually check, is the mean square for treatment correct? Get the sums of squares, divide by the degrees of freedom. So sometimes you can enter your data and make a mistake and include another character in your treatment. So you will have 5 of them instead of 4. That means your degrees of freedom for treatment is going to be different from the true residual degrees of freedom. So in that case, you're able to see whether you're making mistakes in your analysis. The F ratio, we are interested in the treatment effect on the response. So the F ratio gives us the value, the F value, which we can calculate the p-value or compare with the F distribution table, as we shall see. So the F ratio is the ratio of the mean square treatment and the mean square error. So the R package also calculates the p-value corresponding to this F ratio. Then we are able to now interpret our hypothesis. We either reject the hypothesis or fail to reject the hypothesis. Okay, so I'm going to the chart. Are we doing well so far? Somebody say, when you say no, please put a comment why you're saying no. Somebody says not clear, I don't know where I should start from. You need to be specific. Okay. Okay. Excellent. Most people are saying yes, very clear. Okay. Oh. Okay. Let me check the Q&A. Yeah. Okay. Okay, Ezekiel has a question that can Anova actually do when you have different varieties replicated and then you want to test the effect of rainfall on yield? Yes, Anova can do that. You missed Ezekiel, download the videos for the first training. We talked about replication, we talked about blocking, we talked about randomization. So it's going actually to help you know that an isovariance is suitable for your data. Now, somebody says I should talk about the degrees of freedom. Now, I say that for treatment, the degrees of freedom is the number of treatments minus 1. When we are computing the sums of squares for treatment, we need to know the mean, the overall mean for all the treatments. So because of that, we use one information, which we are subtracting here. So the information that is left, it is the free information, degree of freedom, the information which is free for you now to use in your analysis, degrees of freedom. So here the number of treatments minus 1 parameter. Then residual Degrees of freedom is the total observations minus the number of parameters or the number of treatments here. And the total, remember when we are computing the sums of square total, we need the mean for the response, and it costs us 1 degree of freedom. That's why we have n minus 1. So we are left with n minus 1 information for you to deal with, okay? Okay, so I assume that all is well. So can I continue, ladies and gentlemen? Okay, let's continue. Okay, remember our hypothesis. We said the null is that overall there are no treatment effects on the response. That's why it is abbreviated as as mu A is equal to mu B is equal to mu C. This is the statistical way of presenting the population means. But in your research, write it in terms of your research process. Don't write mu A is equal to mu B is equal to mu C. Nobody knows those things. Yeah. Now, alternative is that not all means are equal, or at least one of the means is different. So, alternative could be that there's no variation. I mean, there is variation in or there is an effect of treatment on the response, or there's variability among the treatments. So here I've pasted an analysis of variance table, a one-way analysis of variance table from a package, okay? So the analysis was done. Why have I done this? To show you what happens when you analyze your data using a one-way analysis of variance. What type of output do you get? So we see the source of variation. Treatment is the between variation. Error is the within variation. The degrees of freedom, you can see here we have 3, meaning we had 4 treatments, and the error degrees of freedom, there were 24 observations minus 4 gives us 20, and this should add up to the total. Sums of square, there is a formula we use for computing sums of squares, but if you want that, then you will have to travel to Uganda or meet me in person for us to do the math, okay? But we don't want to go into math now. Okay, mean square, we said it is the ratio of sums of squares and degrees of freedom, and you can check if you have a calculator, just put this value here, divide by 3, you will see it is equal to 430.5. And also the mean square error, get this value, divide by 20, you will see it is 22.8. Then the F ratio is the ratio of the treatment mean square and the residual mean square. So we get this value 18. So you can check through. That's why I'm telling you, when we do analysis, when I'm doing my analysis, I don't just produce things, I check. Actually, I use different statistical packages. I run from R, I go to SPSS, I go to SAS, I go to GeneStat, just to prove that I'm not making mistakes. Then the package, whichever package you use, gives you a probability. And it is 0.0000. Okay? Remember, we said we are setting our alpha at 5%, which is 0.05. Now, if we get a probability of 0.000, it means that the chance that the null is assumed to be correct has reduced to 0.0000. So there is evidence to reject the null hypothesis and conclude that not all means are equal, or there are differences in the means, or there is a significant treatment effect on the response. Now, the analysis of variance, once it is insignificant, it just indicates that the population means are not equal, but doesn't tell you which mean is different from the other. So it is just an initial analysis which tells you that overall we have differences, but now from there we need to know where are the differences coming from. Okay? So let's go ahead. Now, if you're presenting your results, this is what you get in your output, either R, whatever. For this case, let me talk about R because it's what we are going to use. So R will give you an output like this. You don't copy and paste the whole thing in your Word document, okay? Because if you do, if I'm supervising you, I would like you to write about these degrees of freedom, write about sums of squares, write about mean square. It is too much and not even useful. What we want to do is to pick the most important information. So for that case, we will present only this bit in your document. And we are saying there was a significant effect of species on growth of trees. In bracket, I put my F-value, degrees of freedom, and P-value. Yesterday I said that of recent past, journals want you to present the real P-value, not this business of saying P with a less than sign. How about if you're not saying the truth? So we want to avoid people speculating that you are guessing. You put the real P-value. P is equal to 0.000, okay? Okay, so let's go ahead. Now, I say that the ANOVA or analysis of variance tells you that overall, there is an effect of the treatment on the response. But which particular treatment is actually affecting the response? That is when we go to the next slide and do what we call treatment comparisons. Okay, so I want us to go through treatment comparisons. Then we shall go and do some practicals, and then we will come back to theory as the need arises, because I want us to get both today. Today we are ending at 1:30, so we need to maximize our time. Okay, so we have the treatment comparisons. Now, under treatment comparisons, we are comparing the different treatment levels you have. Which level is different from the other? Which one has a higher mean? Which one can you recommend to the farmer? So here we are talking about tree species. Which one do you recommend to the farmer to grow on their farms? Farmers don't want things which take long to grow. They take space and even time. And time is money. So we want to recommend a tree that is going to grow very fast, and the farmer gets their money after 5 years or 3 years, okay? So this statistics here helps us to sort out which particular treatment is better than the other. So there are various multiple pairwise comparisons. There are many. We have least significant difference, sometimes called Fisher's least significant difference. There is a formula there. T alpha, the T is obtained from the T distribution table. And then the mean square error, MSE is mean square error, is obtained from the analysis of variance table. RI is the replicate, number of replicate for treatment I, and then number of replicate for treatment J. So if you have 4 treatments, how many times have they been replicated? Okay, we have a hypothesis that goes hand in hand with the least significant difference, which states that the absolute, if you can see my hands, the absolute from mathematical jargon, the absolute value. So that means that if you subtract small minus big and get a negative, don't mind about the negative sign. So the absolute difference between 2 means if it's greater than the LSD value, then we reject H naught. Okay? So H naught meaning that the 2 treatments are similar, there are no differences, versus 2 treatments are not similar. So as we shall see, there are many pairwise treatment comparisons. We have Turkey, we have Dunet, etc., but they have problems. Some people call them family-wise rate, other people call them multiple pairwise rates. They have problem in that when we do a comparison for example, treatment A is compared with treatment B, and we are comparing at alpha is equal to 0.05. For the first comparison, our alpha remains 0.05. When we go to the second comparison, the alpha changes. When we got the third, it becomes actually bigger. Okay? So that is the problem with multiple pairwise comparisons. So in that case, there is also another option, another alternative, which helps us to eliminate the problem of multiple pairwise comparison. So in that case, we use what we call contrasts, and they are called orthogonal contrasts. I'm going to explain those words. I think they are a little bit big, but we'll dissect them. So before I talk about the contrasts, there are also other methods that control the family-wise error rate or the pairwise error rate, and we can use the Fisher's protected least significant difference, or the Tukey honestly significant difference. And in R, we use the Tukey HSD function, and also there's a student Newman-Coles method, and in R, it has the sync test function. Okay, so that's what we are going to, in R, we'll look at the Tukey and the LSD and then Newman, but there are many. You can choose whichever you want, but whatever you choose, even if these methods I'm talking about try to regulate the problem of increasing significance level, still does not remove the problem. They just reduce, but they don't remove the problem. So we have what we call pre-planned comparisons. These pre-planned comparisons result into orthogonal contrasts, which I was talking about. Now I'm making the things simpler. Okay, so orthogonal contrasts are called they call prior comparisons or pre-planned comparisons. These ones, you actually plan them at proposal stage. Now, the ones we've just seen, let me go back. We call them post hoc. Post means that you think about it after you've collected the data. Yeah, from the word post, it means that you think about it after something has occurred. So these pairwise comparison methods, they are done after you've collected the data. You don't actually plan for them. You just think, oh, maybe there is a significant difference. Now, let me do LSD, let me do Tukey. But the pre-planned comparisons are planned at proposal stage before you collect your data. Okay? So here you state your research questions at proposal stage. For example, the data set that we are going to look at, there are 2 exotic species and 2 indigenous species. So my research question at proposal stage, do exotic species grow faster than indigenous species? So in the growth experiment, species A and C are indigenous, while species B and D are exotic. The other question I'm posing is that, do growth among exotic species differ? Or does growth among the indigenous species differ? So you will find that if you look at the first comparison, we are looking at the average of the exotic minus the average of the indigenous. In the second question, we are looking at exotic only. There is nothing to do with the indigenous. In the third one, we are looking at indigenous only. So those pre-planned questions are independent of each other. And we can always prove whether they are independent. When you come up with pre-planned questions which are independent, that means the resultant contrasts, the comparisons, are also going to be independent. They are going to be orthogonal. Orthogonal means they are independent. They have different information. Question 1 is different from question 2, is different from question 3. That is what we call pre-planned questions. So we are going to see this in details when we are doing the practicals. Okay. Probably we just talk about assumptions and then flip back or go to R and do some practicals. It will become more understandable. Okay, it will be more clear. So we have some assumptions. All models have assumptions. For any model to be valid, the assumptions should not be violated. We assume that the experimental error or residuals have constant variance. We assume the residuals are normally distributed. We assume the residuals are independent. We also assume that the data was either randomly collected or the experimental units were randomized to the treatments. So there is randomization which eliminates bias and also which allows us to perform inferential statistics. So if you collect your data using purposive sampling for those doing surveys, then don't do analysis of variance because your data has bias in it, is subjective. You are already choosing what you want. You know what you want already. So don't do inferential statistics if you use purposive sampling. Or if you, okay. If you specifically choose some treatments and put them in a fertile area, and then the ones you're not interested, you put them in less fertile, that would be biased information. So when you do randomization, it eliminates that bias. You don't know where this particular treatment will fall, and all treatments get equal chance of being applied to the experimental units, any experimental unit. Okay, so lastly but not least, we use residual plots to assess the assumptions of constant variance. We construct a plot of residuals versus fitted values. The fitted values are the predicted values. The model you have, you can use it to predict values. Then construct a plot of the residuals. Residuals, we said it is unexplained variation. We have the total variation, and when we run the model with treatments, the treatment explains some of it, and whatever remains is the residue. In mathematical terms, residue is equal to the observed response minus the predicted response. That is residue. Okay? So residuals versus predicted value or fitted value, that plot, which we are going to see and put more information on it, helps us to know whether we have constant variance or not. Then we have a normal probability plot, which is used to check normality of residuals, and it comes with a p-value. So you're able to know whether your data is normally distributed. Then we also have a plot of residuals versus experimental unit number, and it is used to check for independence of residuals and also randomization. Okay, so those are the things that I want us to talk about, and then we will look at two-way ANOVA. If we finish the practicals for one way and do all that, then we come back, look at two-way ANOVA, look at factorial, look at split plot. I think that is the last part of these slides, okay? But I wanted us to have a feel of what we've talked about in R. Unless if somebody has a burning question, let me go to the chat and see. Yes, some journals want us to put the real p-value, so you will indicate p is equal to 0.00, okay? I'm running out of battery, I'm very, very sorry. Can you look for where to charge the battery, because you're going to miss out on the practicals. Please do, so that you don't miss the practical. How do you calculate sums of squares? SS is sums of squares. It has a formula. As I said, we will not go into the math, but the formulas are there. Even if you Google sums of squares for treatments, you'll get the formula right away. So we won't do that. Let's do the practicals so that we can have a feel of one-way ANOVA. What's the difference between Turkey and SNK? It gives the same results, no difference. They are all types of testing, doing comparisons. Actually, they are t-tests, but very many t-tests, as we shall see. difference between random error and residual. Okay. Somebody is saying, can we report P less than 0? I said it has to be equal to the exact value. If you're reporting P less than 0.001, meaning that your significance level is 0.001, okay? So you're looking at P is equal to 0, but you can get actually the exact value in either R or any package. What analysis should we use for purposive sampling? Just descriptive statistics, numerical summaries and percentages and the graphs only. Okay, let me go to R. Let's go to R, and then we can share those comments. So I'm assuming that you got the notes, and my colleague has done a good job to post the notes. So let me stop sharing this and share the script for R. We are back. I'm assuming that everybody has their R script. It's called follow-up 1, different from my colleague, Dr. Helen. This is about experimental design. And this is a new script, so we will still load our packages, and we are also still going to go and set our directorate. Okay, so I'm running my packages, so do the same. There was a question in the chat that how about snowballing? Snowballing is also subjective, so you use descriptive statistics only. Okay. So I'm setting my directorate using session, set working directorate, and choose directorate. I am going to a folder where my data sets are, the ones I'm going to use for follow-up 1, where you saved your data set, that is now your working directorate. And then click open. So it is set. Oh, somebody says our script is named follow-up Anova, probably. Let me, sorry about that. Let me open follow-up Anova, and thank you for correcting me. Okay, follow-up Anova. Thank you so much. Now I'm in follow-up Anova. I must have updated it, and that's why I changed the name. Okay, but it's not so different. So I'm still running up my script, my library, and then I'll set my directorate to where my data is, and it is in follow-up, and click open. Now we are good to go. So let's go and see what is happening. Okay, so we are going to look at analysis of variance one way. We are going to import our data using the read.cv. I know that by this time you know how to write these scripts, even if we don't give them to you. So probably we give you a practical where you have to write the scripts yourself. So I have read in forest.csv, and I put in forest for me to see what is in forest. So there we are. So let me just make this a little bit. Okay. So now when you put forest, it gives you all the data in the data set. And in this data set, we have species. There are 4 species. We have growth rate. That is the growth of those species. And I told you that in our analysis, we are going to assume, or we know that A and C are exotic and B and D are indigenous. And we are going to do our pre-planned comparisons using those criteria. So then we can actually, if you want to see what is in forest, whether it has, you can use string forest and then run. That tells you what is in, whether your species is a character or not. So I've used str in bracket the object to see what is in forest. Is species a character or a factor? So here you can see that species is a character and growth is numerical. So we want to transform species into a character, and we use species, we call it species again, and we use factor as a function to make it a factor. And we use this object forest, which is the name now of our data set, and call the variable species, which we want to change to a factor so that we can be able to perform our analysis. So then we click run and check whether it has converted using the class species, and it says class species has been converted to a factor. Are we okay up to there? Can I see some comments? Are we fine? I'm using my phone, working on my laptop. Please send email address. Okay, yes, we can use convert. We can use either as factor or factor. Okay. So participants have said yes, 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 excellent. I am so delighted. The participants I'm dealing with are very good. They are excellent. They are quick at understanding, which is going to make us move very fast. So I use the summary function to summarize growth. Okay, so I click there and it gives me the summaries of growth, irrespective of what species I have. So I have growth, the mean growth is 11.4, the median is 26.16, the mean is 26, the maximum is 43.32. So we can write that in we can copy and paste this, put it in a nice table in your Word document, assuming this is your project you're dealing with, and write the overall mean is this, the maximum growth is this, the median growth is that. Then you go back. Sometimes you want to know by species, which species is doing well. So we come to the next step. This one, I said this is a recap. Construct graphical summaries to assess the trends and differences in box plots. So I'm using the dplyr. I'm just checking if it has not been run. I run it again, but it's already there. So in the second line that we have, we can see forest is our object where our data is, and we are using this percentage greater than percentage. That is what we call a pipe, where you pass your information, you're sending your information to R. So you want all that in one go, not to write them as separate information. So you want to summarize forest by group. By group is a function for you to summarize this information by forest. So all this is written in one go, and we are going to run it. And we have our output. How? Okay. So the data is here, the summary I've gotten. We have species A, B, C, and D, and their mean growth. So here I wanted to see summary by mean by species. So we can now comfortably say that species B has the highest mean growth. D is also following B, and the one with the least mean growth is C, which is 19.5. Okay, somebody asked, how can I know that a particular variable is a factor or not? So let me go back a little bit for the benefit. So when we were at forest, you remember when we read our data? We read forest. Forest is the data set, forest.cv, .csv. Then I am naming it still forest and I read it. Then I print it. Then I want to know, if I want to know, you see this command I've written here, I'm going to put a hash, and this is used for knowing the type of data in the data set. The type of variable, let me call it type of variable, better. Type of variable in the data set. So this is the string is used. I'm highlighting in blue for the purpose of that person who is lost. It is str in bracket forest. When you use it, you're able to know what is happening in your data set, whether it is a factor or not. Then if it's not a factor, just like we saw, then we can now convert it to a factor using either as dot factor or factor, whichever is easier for you. Okay, so let me go to the analysis. Is that okay? Should I go to the interpretation? But in box. I have not drawn the box plot, so you should wait. You're going ahead of others. Okay. So let's now construct the box plot. Okay. So we've summarized our data. We are going to construct the box plot, and that is the command. Box growth is a function of species. A data is called forest. You name the x-axis as species, the y-axis as growth. Okay, let me run that. So we get our box plots. They are right here. I'm going to zoom them in. Can you see the box plots? Or I need to share. Can you see the box plots? Yes, okay, thank you. So, I've zoomed. So the box plots, we can see them. We can see species on the x-axis and growth on the y-axis. For your project, make sure growth has its standard units. That is just a by the way. Then even species should be in scientific or using those Latin or Greek names for ABC for your write-up. So here the black line is the median. The black line is the median within those boxes. The first value here, you see, if you go to C, is the minimum value. When you move to the box, the edge, the first edge of the box is the first quartile. Then the black line in the middle of all boxes is the median. The last edge of the box is the third quartile. And the last line on box plot C, which I'm pointing at using a cursor, is the maximum value. And any value that you see, for example, this one here, could be an outlier. Okay? So we can now compare the medians. These are medians. I'm sorry, I'm told you're not seeing the zoomed one, so let me share the zoomed box plot. Okay, there we are. Is that better? Okay, so can you see the zoomed one? Okay, sorry about that. So what I was saying is that when you look at box plot C, I'm just using it for explanation, is that the first part here of the box, where my cursor is the minimum value. When I move, the first edge of the box is the first quartile. This is the median. The black line in all boxes is the median, a measure of average, and then or central tendency. And then we have the third quartile. Then this part here is the maximum value. So the box plots are used to compare between groups. So it's one way of visually showing whether there are differences in the groups. So we can see that if we look at the black lines, there are actually differences. A and C don't seem to be so different, although C is a little bit greater than A. But we can see A and B. B is higher, or it has a higher growth rate compared to A. And as well as B and C, you can see there are differences. And C and D, there are differences. So we want to go now, you can copy this and put it in a Word document and write around it, just like the way I've been talking, that there are differences in the growth rates of the species. We would like to confirm these differences using an analysis of variance. This time no t-test because this is more than 2 groups. Okay, so I'm going to stop sharing unless if there's a question and I go to, the other thing I forgot to talk about is the distribution. If this black line is in the middle and the top part is equal to the bottom part, that means the data is normally distributed. So with the box plot, we are able to see distribution of the data, either normally distributed, skewed to the right, skewed to the left. So you can see that in the first box A, this lower part is the left-hand side. The top part is the right. So you can see the top part is larger than the bottom part, meaning the data is skewed to the right. This is also skewed to the right. The top part is bigger. If we flip this box plot and put it horizontally, you see that the top part is on the right, on my right, even your right, and the bottom part is on your left. So this data also is skewed to the right. This is skewed to the left. You can see the left part is bigger than the bottom part is bigger than the top part. So this is skewed to the left, or to the left. Then this particular one is also skewed to the left because this part is longer than this part. So that's about distribution. You can use a box plot to also show you the distribution of the data. Okay, so let me go to the chart. Any question? Can you please repeat on normal distribution regarding the box plot? Okay, please explain again the pipe. Okay, it is clear. Okay, somebody says summarized growth is equal to, okay, he was trying to answer you how to determine the mean value of a series. Okay. So somebody says I should talk about normality. I'm saying I'll start with that question that if this black line, first of all, the black line is a measure of central tendency. It's the median. So if it's in the middle of the box plot, the top part is equal to the bottom part, then the data is normally distributed. Now, if the top part is larger than the bottom, you can see that this is the left, the bottom part, and this is the right. Okay? So we can see the first box here. The top part is longer. It is longer compared to the bottom part. So meaning that this data for A, species A, is skewed to the right. If we go to C, the bottom part is longer than the top part, meaning this data here is skewed to the left. So that's about skewness. Then about the pipe. So I'm going to stop sharing here and go to the R command. Then I can now share the R command and talk about the pipe. Okay. So we use a pipe when you have so many commands that you want to write in one go. You want to run them at a go. So that's why we use this pipe. This is called a pipe. Percentage greater than percentage is a pipe. It's like we use a pipe to carry our water from flat A to flat B. So instead of using various pipes, we use one pipe to supply all the streets. So this is the same thing here. So we are using one pipe to join up two commands, which we would have done in one command. Okay? So we have the object and we are summarizing by species. Then we are also asking the summary to be for growth. Okay? And it is the mean that we want. Okay, so that was about the box plot. Another way you can use to construct the box plot is by using the ggplot. So I'm going to run, so let's all go to the ggplot. You put your cursor wherever you want, in the middle, at the bottom. You can see that it is a gg function. You're including forest, that is the data. AES, that is to make it beautiful. You say X, this is the label for X. Y, growth is the label. And geo box plot. Okay, so let's run it and see what happens compared to what we had. So remember we had something like that in our bottom right. Now we are going to have something different. So let me zoom it and share. So I'm going to share again. So it is a box plot again. The only thing I have done is it has this grid. I think it's more clearer than the first one. Yeah, it's more beautiful. That's why you see it's a gigi and they put in AES, meaning make it more beautiful. Aesthetics, that word. You know, when you didn't study the nursery, you can't pronounce some words. So, you know, I didn't see the nursery school, so okay, let's go ahead. So the same explanation we can use for this box plot. It's just another way of constructing the box plot. So I'm going to move out of there. We don't need an explanation. I just wanted to show you that actually we can use different ways of constructing the box plot. So we've now seen our summaries. The most important bit of summaries is to know whether there are differences in magnitude of the different treatments you have, whether you really need to go and run an analysis of variance. I think we see that there are differences in the different species and we want to run an analysis of variance and check for those differences. So let's go to one-way analysis of variance. And I said we use one-way analysis of variance because we only have one factor, which is species. Okay, so you see here, the person who was asking, how do I know that forest, the data forest, how does it look like? What type of variable do we have? Is it character? Is it numeric? Is it a factor? So still here I come and ask R to find out what type of data I have. It says species is a character and growth is numeric. You see it has changed. We need to find a way of making R store what we've already done so we don't have to redo it. Okay, so now, again, I'm going back to converting species to a factor. So I use species, factor, species, call the species name. So it is being converted, and the next line I'm calling my object status.anova. It is not a function. It's just an object that I chose to use. You can call it your name. You can call it Helen or Susan or Tom or Richard, or you can call it Yusuf, etc. Whatever you want to call it, doesn't make a difference, just an object name. So I've called it status.anova. And the function is LM. LM is linear model. And our linear model is the Y, which is the response is growth, is a function. This squiggle you see is function of species, meaning that growth depends on species. And our data is called forest. So I'm going to run that. So when I run it, I don't get the output. I only get the output if I call this object. Okay. The other thing is I have added another function called Anova, which I can use to calculate the sums of squares and degrees of freedom. Okay. So before I go to that, let me just show you what is in status. Status, I hope you're seeing what I'm doing, Anova. So then I run that. So it gives me the output that I had calculated with that command of GLM. So let me just first of all show you that actually there's something going on. So we have this, it gives you the coefficients. It gives you species B, species C, and species D. But we want the degrees of freedom, the sums of squares. So I've added a function Anova for that object status. It's what I'm going to run now. So when I run it, I get now my analysis of variance table, which we've been talking about. So let me bring it up here. So this is the analysis of variance table. In the bottom left corner, you can see it is written on analysis of variance table. The response is growth, degrees of freedom. You remember this is the same type of analysis we had when we were talking about our theory, and it's the same thing I brought here. So we can see degrees of species. There are 4 species, we remain with 3. Now here you're checking whether the package R has done the right things. We had 4 species and we have 3 degrees of freedom. So our data, our analysis is correct. We can go ahead to interpret. Remember I said that we need the F value, degrees of freedom, so we can have our F value and P value and degrees of freedom to take into our document that we are writing, our thesis, our paper, our journal paper, our magazine. Okay, now the hypothesis that we are testing under GLM is that overall there are no species effect on growth. Overall, there are no species effect on growth. Or alternative is that there are differences in the effect of species on growth. Growth is our response. So now, remember our significance level is 5%, which is the same as 0.05 in terms of probability, or in terms of, okay, 0.05. Then our calculated probability, you remember some people really didn't want 0.00. Now it has calculated for you the real probability, which is 4.674 times 10 to the power 6. So it is equal to 0.0006 decimal places. Okay? So you can write it in an expanded form and round off a few decimal places and put it in your Word document. So this p-value here is less than 0.05. So we have evidence to reject the null hypothesis and conclude that there are differences in the way the species affects the growth, or growth depends on the species that has been planted on the farmer's field. So some species are going to grow faster, others are going to grow slower. So that is the species effect we are seeing. Or we can say there is a significant species effect on growth. Then in bracket, you put in the result of the F value, the P value, and the degrees of freedom. Now you can see these stars. You've seen the stars, star 1, 2, 3 stars. They are telling you that actually this result is significant at 0.01%. Okay, that's what it is telling you, the stars. Okay, let me go to the chart. Can we go ahead? Is everything clear? Anova dot this says okay. Is there Anova for CRD load? Okay, so I have seen a few questions. Somebody says he got an error. Please highlight the error in your console, paste it in Google, and you'll get a comment. Because if I don't see the error, I cannot really help you. But highlight the error and paste it in Google. There are so many people who have gotten that error, and there will be help for you. Then somebody says, I should explain more about the stars. Below here, you see significance codes. Have you seen them in the output? The significance codes, we have 0, star, star, 3 stars, then 0.00, 2 stars, 0.01, 1 star, and then 0.05, 0. These are levels of significance. Yeah? Remember, we chose 5% and 0.05. So our result is significant at 0.5, but it is also significant at 0.001%, which is the one with 3 stars here below here. So that's what I said. Somebody says I should talk about the box plots. Now, box plots, I'll talk in the theory that they are used to compare groups. If you want to see whether group A is different from group B, we use box plots. Box plots are 5-point summary. They include the minimum value, the first quartile, the median, the third quartile, the maximum value. The median is the measure of central tendency. So the black line in the middle of a box plot is the median. So you can compare the medians to see whether there are differences in species or in treatments or in any factor that you're testing. Okay, so that is the box plot. So let me go and see comments before we go ahead. Is there any function that can help? The questions are running very fast, so I can't catch up with them. How do you allow the effect of other factors in ANOVA? Okay. Then, yes, it is significant at 0.01. Great. A Gigi plot, red error. Did you load Gigi library? Please make sure your Gigi library has been loaded. And error in call pellet. Oh no, I've not used pellet too, have I? It seems you're going ahead of me. So the right package is ggplot2. Please make sure you install it and then load the library. ggplot2. And I'm looking at the comments in the... Okay. Okay. Okay, so it says the stars here. Okay, so somebody is saying that the stars, the 3 stars is for 0.01. That is very correct. And 2 star is at 0.01. and 1 star is at 0.05. Thank you very much for the correction. I hadn't seen that. Okay, I think those are the questions. Whoever has an error, you've had the ggplot2, make sure you install and load that library, and you'll be good to go. Somebody has said, is there a special ANOVA for CRD? Actually, CRD can either have one factor, so we can run a one-way ANOVA. You can have two factors in a CRD, and you may end up running a two-way ANOVA. Okay? So those are the questions I saw. Now let's go ahead. So alternatively, if you can use the OV function, AOV function, to run an analysis of variance. So species is the name of the object, and AOV is the function telling, and I'm telling it that the model I want it to run is growth is a function of species and data is forest. So let me run that. And then I do summary, and we see that it is the same output we got as before. So I just wanted to make sure that whatever makes you comfortable, please go with that, but you get the same results. So since we've gotten a significant species effect on growth, we are now going to do multiple comparisons. In your research, if you find that the p-value is non-significant, then you just report the result that there is no species effect, but don't do multiple comparison tests. I repeat, if your data set gives you a non-significant result, meaning your p-value is bigger than 0.05, meaning there is no overall effect of treatment on the response, don't run a pairwise multiple comparison test. We only run it once we found out that overall there is a treatment effect, and you want to find out which particular treatment is actually significant from the other. Okay? So let's go ahead. I told you that multiple comparison tests are called post hoc tests. They are not planned for. When you get a significant ANOVA, then you can say, let me use them. So LSD is the first one we are going to use. The function is called LSD.test. And on the other hand, when you don't understand anything, you can actually ask R to help you. Just put question mark LSD.test. Then it will tell you what LSD.test is. So I'm naming the object of this result as LS, and the function is LSD test. Species is the species, that is the model which I last ran for analysis of variance. You remember, let me take you back. The model is right here, which I've just run. The name of that model is species. So it is the one I'm calling here. I'm telling R to run an LSD test on the model species, but in particular, look at the species, which is the treatment. So let me run that. And I print out species. So let me just enlarge it so that we see our species. So if you look at the bottom left-hand corner, we shall see that we've gotten an output. Okay? We have A, B, A, D, A, C. You've read many journal articles and you find them with a nice drawn table, and they say underneath they put note, means with the same letter as not statistically significant. I repeat, they put a note below the table that means with similar letters are not statistically different. So this is what R has done. It has attached the letters for you. You can see these letters here, the small letters. you can actually make them subscripts on the values of means. So we see that if we look at A and C, they have the same letter CC, meaning that A is not significantly different from C. And if we look at B and D, they have different letters, meaning B is significantly different from D. So the average growth rate for D is significantly higher. If you look at the magnitude, 37.4, is significantly higher than the average growth rate for species D. And when we look at B and A, because A and C are different letters, the average growth rate for B is significantly higher than A, species A. Then if we look at D and C, the average growth rate of D is significantly higher than A and C because B has a different letter from species A and C. Okay, so that is about the mean. Now you're finishing your analysis. You want to tell the people that there are differences. What is different? B is different from all the others, but A and C are not statistically significant or different. Then we can now say that species A has the highest growth rate, so we recommend species A for planting in our fields. Okay, so you've made a recommendation, you made conclusions, and you've also made a recommendation for your project. And also recommendations should go hand in hand with your results. They should be similar to your results. Don't get a recommendation which looks so nice from somebody's paper and then you paste it in your results. That is not your recommendation. So I have just said now I can make a recommendation that the farmers can now grow species B because it has a higher growth rate. And now you even have the type of soil where they grow best. You can put in more information. You are in the discussion. You can tell us why species B is growing faster than DAC. It could be due to maybe it is acclimatized to the environment, or you can talk a lot about growth. Now the statistics is done. It is about the biology. We now marry the statistics and the biology. Don't run your table. You have nice tables from R, and then you can't write around them using the biology. You should go read your literature and see what others have done. Is it what they got, or mine is different? If it is different, don't refute your results. You say my results are special. Become unique, okay? So tell them your results are special, they are different, and that's what you stick with. Don't change goalposts. You know, we want always our results to be similar to so and so. No. What your experiment has is what you should present in your project. Okay, is there any question? Let me check the chat. If there is no question, we are going to go ahead. We can draw a box plot, yes, with letters, yes. But the marriage between biology and statistics is equal to a journal paper which can be published. Thank you. Okay. It says could not find, it says could not find LSD. Which one? For those who can't run LSD, it should be dplyr. You must install dplyr, I think so. Or install Tidal. So check, you see I had a list of packages and I installed them for that purpose so that my functions don't refuse to run. Okay, even Agricola has, even Dewey, okay? What is the maximum factor levels in pairwise comparison? There's no maximum, but the problem is pairwise comparison, which you have not done anyway. I told you has a problem. The more comparisons you have, the more the significance level increases, and there is a formula for that. Okay, you can always prove. At comparison 1, you have 5%. As you go to 2, it keeps on changing. The maximum number of levels, you can have a formula. It is the number of treatments. Please write down. I don't know. Okay, it is T into T minus 1 over 2. That is the maximum number of comparisons. The number of treatments into open brackets T minus 1, close the brackets, over 2. So let me write it in the, let me write it right here, down here. Hopefully I can write it. Okay. So here I am. I'm going to put a hash. So number, maximum number of comparisons equals a number, T is number of treatments into T minus 1. Okay. Then divide by 2. So that gives you the maximum. So we have 4 treatments into 4 minus 1 gives you 3 times 4 gives you 12. Divide by 2, we have 6 comparisons for this particular example we have. Okay. So we can also draw a box plot. You just go to the box plot. We have 17 minutes. And Helen, I'll leave 10 minutes for Helen to make some announcements. So let's go through the honest comparison so that let's draw this box plot or bar graph with the, you can actually, instead of having the output for means with the letters, you can have the means on the bar graphs. As you can see, let me zoom it out quickly. Stop sharing. This is the same information as LSD test. If you don't want to present it as a table, you can present it as a graph. You can see this is A, B, C, C, the letters, then you can interpret them. Okay, that is just another way of showing you how to present your data. Or you can actually use box plots, or you can use error bars. Yeah, we did that in the first training. We had error bars on top here. Okay, so you can listen to the videos we used in the first training. You will see how to construct error bars on the bar graph. Okay, so quickly let's run to pairwise comparisons. And I'm going to start with honest. And for you to be able to do this pairwise comparison, you follow the Anova model. So I brought the Anova model here. That's the first line, so that we don't get lost. And our object where we are storing the model is called species, and I'm running it. And then I'm running species.turkey is the object, not the function, and turkey HDS is the function that's going to give you the turkey test. So when I run that, and then I run the object species.turkey, I get the result. So let's look at the result quickly and see how different they are, but the same things. So the results, if we look in the left bottom corner in the console, you can see the results of turkey test. They are different from LSD, but they give the same interpretation. You can see they are saying that A minus C are not significantly different. As we interpret, let's also look at the graph. The graph also reminds you of the results we had in LSD. You can see A and C had the similar letters and they're not significantly different. Even here, A minus C, the difference in those means is not statistically significant. You can see the p-value I've highlighted in blue is 0.983. It's greater than 0.05. Then when we go to D and C, you can see D and C in the graph in the right corner. They have different letters, meaning they are statistically significant. Even here, if I highlight the comparison, we can see that they are different. Now, when you're presenting your results, you can choose to make this a table and present your results, or you can actually bring the means and put the letters as we saw in LSD. Okay. So I'm going to leave that for you. Then let's look at the next test before my time runs out. That is an alternative of doing the Turkey test using the multi-comp view library. That one I won't take you there. You'll practice it in your free time. But let me go down here. I think let's look at the pre-planned comparison only, so that when you go back and I send you the exercise, you'll be able to work out the pre-planned comparisons. Remember, I said that species A and C are exotic, while B and D are indigenous. The first question we had in our theory was the growth rate of exotic differs from indigenous. So we've awarded these coefficients to help us calculate the difference between the mean of the two species. The first one here, a half, it is positive, it is for species A. Let me highlight it in blue. So I'm telling R that fit a contrast for species the model, and it is for the species the categorical variable. And in this species, I have 4 treatments. I want you to assign a coefficient, which is a half, to species A, and then assign minus a half to species B, and a half to C, and minus a half to D. Why? I am getting the average of the indigenous minus the average of the exotic. That's why A and C have positive. So I'm getting the average mean of A plus the average mean of C divided by 2. That's why you see the halves. And then the average mean of B and D. That's why you're seeing the halves and negative. The negative is representing the way I'm saying that exotic differ from indigenous. So the average growth rate, if I put A and C together, subtract from B and D, are they different? That's why you see those coefficients. Then I have another line where I'm comparing only A and C, which are the exotic. Does the growth rate differ among the exotic species? Okay, so this is line 2, where I've awarded the coefficient 1 versus 1. This one's for me to be able to compute my differences, the coefficients. And then the coefficients also help me to prove that these comparisons are orthogonal. There is a formula. If we add them up, we'll get 0. And if we multiply across them, we will also get 0. You can see how my cursor is moving. If I add positive 1 and minus 1 and plus all these zeros is equal to 0. Even on the top, if I add a half plus minus a half plus a half plus minus a half, I'm going to end up with a 0. Now, here in the second part, I'm only concerned with exotic species. Although species has A, B, and D. So B and D is awarded 0 because they are indigenous species. And the exotics, they are the only ones I'm concerned with. So I'm looking at the average growth rate of the exotics only. In the last fit statement, I'm concerned with B and D, which are my indigenous species. That's why I'm assigning -1 and +1. When I add those coefficients, I get a 0. And also when I multiply across, if I multiply -1/2 times 1 times 0, you end up with a 0. So if you go like that across and add all of them up, you must add up to 0 to give us independent contrasts, which are also called orthogonal contrasts. Too much information. Probably, should I stop here, Helen, or I use another? We don't have time, is it? Okay, ladies and gentlemen, tomorrow I'll start with this before Helen comes in with the regression. And then once Helen finishes regression, we are going to look at factorial and look at split plot, we look at repeated measurement, and if time allows, we also look at multivariate. Okay, so that is the schedule we have. So for now, let me stop here. I am going to send an exercise online after this training. It will reach you before the day ends. Okay? And then tomorrow we'll see what people can do and also do this pre-planned comparison and we close. Unless if you have a burning question, I want only to give you 1 minute, but I am so grateful that you've been so attentive and participating. Contrast not clear to be clear tomorrow. Okay? So a survey monkey has been posted. Please, in the chat, click on it and answer the questions. We need those responses to see how we can improve the training. Please, Helen, continue posting it several times so that people can receive. Post it even in the Q&A. The survey monkey is for evaluation. Please click on it and answer the questions for the good of both you and me. How can we improve the training for you and me? Thank you so much. You've been so great. Okay. Okay, thank you, excellent. And you've been very excellent participant, but I have a request. Please answer the monkey, put in whatever you feel, and it will help us to improve the training. Post it again. So just click on it and answer the questions quickly before they turn off. We have 6 minutes, 6 minutes left. And I continue thanking you. You've also done a great job. You've been very great listeners. Even if I'm not on the board explaining, you're understanding. And I'm so grateful. You're awesome people. So the monkey survey has been posted again. Please give us your comments. We improve. Give us the comments to improve the training. We have 5 minutes of filling and send filling. I can't access the monkey. Please post it. Just click on that link. You will access the monkey. Our previous training, we've already posted the previous training, but we'll post them again on your emails today. If you've not registered, I don't know. If you've finished, send it on our email, isn't it? Where does it say? The evaluation. If you finished, the response are being recorded automatically. Don't worry about it. Please check the Q&A. Okay, I really check it. Oh. Somebody has written they need slide for. Okay, you need slide for. Can you set up the link? Zoom link? The Zoom link. Yeah. Quick, we have 4 minutes. as you set up, let me set up. Let me also try to set up. If you don't get the Zoom link, we will send it on your emails if we run out of time, but let me try to set up the support link. I'm going to try and see. Oh, it is the same thing as yesterday. Okay, let me go and copy and send it. Can you send it? I can't see. Oh, okay. Let me check. Oh, there's only a meeting ID. There's only a meeting ID. Mm-mm. Ah, we'll send in their emails. We'll send in their emails. So what are those? Day 1 and day 2? The videos have been sent for day 1 and day 2. And they were also sent yesterday. So I create a quick one? Yes. We have 2 minutes. 2 minutes. Okay, we'll send the one of today when it is ready. For those who need help, please you get the link, support link. We are going to send it either on the chat if we still have time, or on your emails. So we will get the support link. Have you gotten it? Yes, that's the support link. Okay, the support link has been posted. Post it again, quick. The support link has been posted, so please copy the meeting ID and passcode. Yes, we have at 2, we will be supporting you, so log in at 2 for more help. Somebody wants a PhD in statistics. Okay, we shall help you if. So get the meeting ID and just click on it and it will open. So if you click on it, it will open. Okay, done. Eriwa yodda. Ate bwe giteeka wansi badooza yavuddeko. Nkola bukatudi nga bandaba. Okay. Now we are still on.